Alright, silly people, here's the situation. We're going to be calculating the intensity diffraction pattern for a telescope, and it's going to be a bit of a longer problem. But first of all, the first part is to actually have a Python function which correctly calculates the value of a Bessel function using Simpson's rule, just using all the definitions that are given in here. And so that's what we're going to do first. So I am just going to start off by defining the, not actually the Bessel function itself, but instead the integrand of the Bessel function, which I just called Bessel integrand. And it has to be an argument of m, x, and theta. So it's mx theta. All these things will be figured out in a second. And it has to return the cosine of, and I better import numpy as np so I can get the cosine of m times theta minus x times sine of theta, right? But then we can get into the function which is j of m and x, where it actually does the Simpson's rule calculation. So it's n equals 1,000 points for this one according to the problem statement. The integral is always a equals 0 to b equals pi. Just going to use numpy's version of pi. And so h is going to be just b minus a over n as well. Not that. And of course the first line of the Simpson's rule integral is to do the function, which in this case is Bessel integrand. And then you want mx a, right? The integral that you're varying over is theta. So this is mxa plus Bessel integrand of mx and b. And then you do the loop of the Simpson's rule stuff. And I'm just going to sneak back up here and take a look. Yeah, so I'm just going to steal this actually. Yoink. But then I'm going to, fix it with our current situation in mind. Yeah, but this is the general like Bessel or Simpson rule integral. I'm going to change the f to Bessel integrand, and then the last argument is theta. Mx has to be in there. Same thing for this guy. And this is going to be mx in there as well. So that is cool. And of course, you want to return the value of the integral itself, which is going to be for like a Bessel function, or for like a regular old Simpson's rule, you would do h times s over 3. But also, notice that the value of the Bessel function is divided by pi after the integral, so I'm also going to stick a over np dot pi in the denominator there for when it returns. Right. And then finally, we're going to use this program to make a plot on a single graph of J0, J1, and J2 from 0 to 20. So let me go ahead and import matplotlib.pylet or pyplot as plt, and then do a x equals numpy linspace 0 to 20. Might as well make it 1,000 points, and it's just going to plot J0, so J of 0 and x, and then I'm going to label each of these. So label equals, in quotations, J1 0, and then the next few plot lines are going to be the same. It's going to be this guy except 1 and 1, and then this guy except 2 and 2. And then after all those are plotted, we'll do a legend just there. Let's see if that runs. Yeah. So yeah, those are the Bessel functions, J0, J1, and J2. And it's interesting that it's showing 0 to 1,000 instead of 0 to 20. Did I do linspace wrong? No? That's interesting. Don't really know what's going on there. It should just show 0 to 20, but for whatever reason it's showing 0 to 1,000, but that's fine. We can move on to the next part. Make a second program that makes a density plot of the intensity of the circular diffraction pattern of a point with light source lambda equals 500 nanometers. Okay, sure. Let me just take the Bessel function code that we're going to use for this and stick it in a different cell. And it wants to do, obviously, this equation, that I of r. So let's actually just make that a new function all by its own. Def I of r, where it's going to do the J1. First it has to calculate what k is. K is always going to be the same. It's going to be 2 pi over lambda, with lambda equals, I just realized that that's a Python function, but yeah, it's 500 nanometers, so 500 times 10 to the minus 9, where the math is involved. So k is numpy pi divided by, or 2 times that anyway, divided by lambda, and then it returns in parentheses j1x, but it's not x, it's k times r, right? But then the function is divided by k times r and squared. So that should do for I of r, right? Again, it wants a radius from 0 to 1 micrometer. So what I'm going to do is I'm going to create a list of x values to run over from, it's going to be a linspace, just like before. It's going to go from minus 1 micrometer, so 1 e to the minus 6, to positive 1 micrometer, so 1 e6. Just 100 points, because otherwise it does take a really long time to run. Same thing for y. I'm going to do numpy linspace, like literally the exact same line of code, actually. 1e minus 600. I better put a minus 6 here. Okay, cool. Then I will be a numpy array. I'm going to make it zeros in the shape of 100, 100, and with the data type equals, floats. That is just so that you have a grid that is, every grid point on the I is representing a x and y component, and we're going to fill in what the intensities for each of those coordinates are as we go. So for I in range 100, and then for j in range 100, this is just so we're going through every grid point on the I array. You calculate I of r, and then r needs to be calculated. So r is going to be the square root of x squared plus y squared, so we have to do x indexed I squared plus y indexed j squared. Right, and then it will calculate I of r, and then it's going to make it so that I indexed ij is equal to I of r. And then afterwards, you just do the imshow with I as your argument and C map. This is just part of the hints for this problem that Mark Newman gave us. He suggests the color map hot, and he suggests making the argument Vmax equal to 0.01. Apparently those look really nice on this. And just give that a go. Whoops. NumPy array object is not callable. I see. I think I should probably call this something else. Let's call it in instead of I, because it's an intensity. So just to differentiate the array from the function. That seemed to have worked. Okay. Yeah, it's going to take a second because it's doing 1,000 times 1,000 grid point, or no, 100 times 100 grid points. So like 10 to the 4 grid points. But then also for each of those grid points, it's doing a Simpson's rule integral with 1,000 points in that range. So it took a second, but now we have an image, and that's even how it's supposed to look. So quite chuffed at that. All right, looks good.